I am Ed Sperling. I'm the editor in chief of Semiconductor Engineering. I'm here with Bryan Schackmuth from Nordson Test and Inspection. Going to talk today about acoustic wafer inspection. So, Brian, we've heard about acoustic wafer inspection for a long time. What's changing here? What's happening now that didn't happen, say, a couple of years ago when we were using this?
Sure. So the big things that are changing is the need for more resolution. And when you need more resolution, you need more scan time. It takes longer to get the data. The system we'll be talking about is a new type of scanning method, a rotational scan, that allows us to get a lot of data a lot faster than previously.
And that data is, and that resolution is absolutely critical because you're now dealing with much finer features. You're going into packages that are much tighter lines and spaces between them, right?
Yeah, exactly. So as the bumps get closer together, more IOs on the device, the smaller the gap they want to see. So if there's a defect that spans the bridge between two solder balls, that's a critical type defect. And yes, everything's getting smaller as we go forward.
Let's take a closer look.
Sure.
Brian, what are we looking at?
What you're looking at on the right hand side is kind of the actual scanner mechanism. You can see an arm reaching out that holds the acoustic transducer. And then you can see the grooves, that's a wafer chuck that would hold the wafer. And then the way we're scanning on this is a rotational scan. So traditionally, acoustic microscopes would use a raster scanning pattern, like an XY type of pattern. We're using a theta scan, so it's a rotational scan. So there's no turnaround time. It's a continuous scan that's not stitched together. And that's what allows us to get the really high throughput. So kind of the main thing that most customers are looking at, like at 100 microns, we're getting 41 wafers per hour. The previous systems were getting somewhere in the 5 to 8 wafers per hour. So, there's a big multiplier in the throughput we can achieve with this method.
Is that all because you need higher resolution for just smaller features, or is it also because now you're looking inside a package saying, hey, we have all these different things? We have heterogeneous integration going on here with lots of different chiplets.
Yeah. So as they stack for like HBM, they'll have a 8 stack, even up to 16 stack through silicon via, and depending if it's the type of bonding. So there's like a thermal compression type bond, or there's like an underfilled, molded underfilled type bond. The feature sizes in those various methods for HBM vary, but essentially, as time progresses, they're going to be getting down. So right now, we're going down to like 10 microns is kind of our finest scan pitch at this time.
How does this compare to something like X ray, where you're really digging into what's going on inside the bonds itself?
Sure. Yeah. Good question. X-ray is a through transmissive type inspection. It has higher resolution, so it can go submicron. But X-ray is relying on variation in density. So silicon is quite transparent, but the solder balls or the connections would be visible for X-ray. But in between two die, if there's a separation of air, we call it like a delamination, X-ray would just blow right through that, and it wouldn't see that type of delamination. So acoustic, one of the key features of acoustic waves is they don't travel in air. So anything above 10 megahertz and higher, it can't propagate through air. And so once we see an air gap, we get 100% reflection. So acoustic is very sensitive for delaminations or cracks. All the material is there, it's just separated.
There's been a lot of issues around the edge of the wafer. That's become much more important, particularly as the density rises, as the cost of this goes up. How does this play into the finding the defects there, finding potentially cracks and chips and things like that?
The way we're scanning the wafer with the rotational scan, we can set up a region, just the perimeter of the wafer. So just that outside ring. The reason customers are interested in that is the CT or coefficient of thermal expansion changes across the different materials in the wafer. That effect is greatest at the edges. When we were looking at standard flip chips, that was always the perimeter solder bumps. Same story here in wafers, it's that edge. And so what we can do is we can scan that edge at a higher resolution to see finer detail. And then maybe we scan the center area, which is a bit easier to bond. the lower resolution. So we can really optimize the scan time around the customer's requirements.
So with this, you really have the ability to zero in on a piece of the wafer, right? A particular zone within that wafer.
Yeah, so in X and Y, we can vary the scan size and look at different regions. But with acoustic, you can also vary it in the Z dimension. So we can look at the top few layers or the middle layers or the bottom layers. We set what's called an electronic gate based on the time it takes the ultrasound. We can set it for a specific time period in the wafer, and then we can isolate just that layer. So if you're more interested in defects that are deeper within the wafer, we can focus the ultrasound there and show those defects with more contrast and resolution.
So if you think about this whole hierarchy of inspection where you have go from optical all the way up to X-ray, where does this one fit in?
Yeah, so it's complementary, I would say. So optical is going to be anything on the surface that would be visible. You're not looking in the sample. X-ray is really geared towards that density change and looking at those changes, more like the solder balls, metal traces. And then acoustic is very complementary with X-ray. So we're able to see the core more of the cracks and delamination. So I would say most customers are still going to be doing all three of the inspection type of those three inspections.
As we start getting into things like backside power delivery, which is happening on the wafer as
Mhm.
well, does that now fall into the acoustic inspection realm?
I haven't personally seen that in a wafer yet, but I've seen papers on it. Basically, yeah. So we would need to just penetrate deeper into the wafer. So one other thing about ultrasound is the higher the frequency, the better the resolution. So we might be using 230 megahertz, which is our higher frequency. You can detect features of 10.5 microns in that region. But if you need to go deeper in the wafer, we typically will lower the frequency. So we might drop down to 100 megahertz or 50 megahertz to penetrate deeper into the wafer to get to that backside power distribution.
So, in addition to being able to zero in on a piece of the wafer on the X and Y axis, you now can go right through it into wherever you need to go, right?
Exactly. Yeah. So, I mean, ultrasound, it takes time to travel. So there's a speed of sound. Silicon has its own velocity. Copper has a different velocity. So the different velocities will equate to different times. And so we just pick if you have, let's say, 750 microns of silicon, we know exactly in time how long it's going to take the ultrasound to travel that distance. And so we can just isolate, let's say, the back surface. Back,
Does that change with different materials like gallium nitride and silicon carbide?
yeah. So typically, you could say the higher the density, the faster the velocity. So, like your silicon, gallium arsenide, gallium nitride, those are harder, high density materials. So you'll have a faster speed of sound. Whereas, like if you have a molded wafer with molding compound, that plastic molding compound is a much slower material. So because it's a softer type polymer material.
I mean, how about for things like fill? That can be many different materials, right?
You're referring to like the underfill where they have different filler
Yes.
particles. Yeah. The density of that is kind of variable. It falls within a range like 3 millimeters to microsecond, maybe up to 5 millimeters per microsecond. If you have a known thickness of the material, we can characterize it and get the exact velocity.
What are some of the problems that you've had to address as you've been working with this technology? It's been around for a number of years, right?
So one of the things we really wanted to tackle on this machine is to optimize the uptime on the machine. So this system has four scanners, so four scan modules. Each of them are using that rotation scan. And we've made it modular. So you can be performing PM or preventative maintenance on one of the modules, and the other three will continue to scan. So we can really minimize downtime on the machine. And then also having four scanners allows you to do multiple lots. So you can continuously run lots through the machine without having to wait in between lots.
This is sort of like doing things in parallel, right? I mean, that's really what the whole goal here is throughput.
Correct. Yeah. Throughput is paramount. Again, when you go to that smaller defect size, it takes more time to get the data. And so multiple scanners with the rotation scan is the way we can achieve that UPH or throughput.
As you do these multiple scans, can they also do multiple scans on one particular area over time and start showing up, hey, we found a defect here that we didn't expect to see before?
Typically, I mean, we're just looking at the wafer, after it's been processed, the bonding process or the annealing process. So we are using deionized water. So as I mentioned before, the ultrasound won't travel through air. So we use pure deionized water to couple the ultrasound of the part. And I would say in traditional type scanning, the wafer is immersed in a water bath. Here we're using what we call waterfall. The water basically like a bubbler bubbles over the wafer. And so we minimize the water. And so we don't expect to see changes over time. In the traditional method where you immerse the wafer, you could get what's called like ingression of water into the layers. So that was one of the things, we're trying to avoid with this machine. But we typically, if we look at a wafer, we more than one time, it would be pre-process and then post-process, and then we would look for the changes. So did the defects get larger because of some thermal process that was done on the wafer? And then we can use analysis to qualify the percent delamination or percent defect, number of voids, size of voids. And so we can track those changes in that same wafer over time.
Is it just one inspection point, or are there potentially multiple insertion points for this?
So there would be potentially multiple. So in the processing of the wafer, there might be stages where you have a temporary bond, where the wafer is bonded to a substrate just for processing. We might check that temporary bond because it's critical in the processing that there aren't defects at that layer. If there's a delamination between the substrate and the wafer, it'll cause somewhat of a blister or a bump in the wafer. And so if you're doing a mechanical processing, those have a tendency to kind of explode and you'll get a breakout on the wafer. So we might check it during that temporary bond. And then when that bond is removed and it goes to another permanent substrate, we could check it again at that point.
What's the direction here? Is it really just to inspect on the wafer itself, potential cracks, or can you potentially also look at, because you're now on the Z axis, hey, we've got warpage over here that we didn't expect?
Yeah, that's a good question. In our current roadmap, at the end of this year, early next year, we'll be implementing a feature called QDZ, which is quantitative dynamic Z. Basically, what that means is for a warp wafer where the surface is not flat, typically you're talking about plus minus 3 millimeters of warpage. What happens is as the warpage of the wafer changes over the spot you're looking at, you need to adjust the focus to follow the contour. And so the QDZ is really real time following of the warpage to maintain a good image across the surface. Because the ultrasound travels at a certain speed to reach the surface of the wafer, we can also measure that and then we can map out the curvature of the surface of the wafer. So we can, at the same time we're inspecting for voids inside, we can map out that kind of surface curvature.
How much warpage are we looking at here? I mean, this is really very almost undetectable a lot of times, right?
Yeah, for semi spec, I think it's around 100 microns. That's kind of their target. But when you get into the molded wafer, that molding process will induce a lot of warpage. So we've seen, I think, worst case, about 3 millimeters of warpage.
And that puts all sorts of new strain on this device, which you didn't have before.
Correct. Yeah. And one of the things, so right now we have the wafer chuck we currently are using will take the warpage out of the wafer. So if there's a few hundred microns of warpage, we apply a vacuum and it basically flattens the wafer. Some customers are okay with flattening the wafer if it's a minor amount of warpage. When you get into that 3 millimeter range, you don't want to flatten the wafer with suction because you might induce stress on it. So we're moving to like a 3-pin type wafer chuck. The warpage stays in the wafer and we optimize on that based on the QDZ or that dynamic focus.
This all feeds into where do you actually singulate the individual die in the wafer?
Exactly. Yeah. Yeah.
Where does AI fit into this? Obviously, it's getting a bigger role all the way through manufacturing.
Yeah, exactly. In the system we're looking at, we're generating images. And traditionally, we've used a threshold to analyze those images. So if a pixel is bright, it's above a certain threshold, it's a defect. With the complex structures of today's parts, that simple threshold type analysis is no longer possible to capture the defects. So we're using now AIML to take the different layers. In this case, I'm showing three different layers. The AIML takes those three layers and combines them all into one image. And then we're using machine learning to teach it what are the defects. So there might be features in these samples that are a brighter pixel might be the same brightness as a defect, but we can, using AIML, we can teach it, what the defects are. And then through a learning process, it'll develop a model based on that. And so we can use that model to do the analysis of the wafer.
And so you combine this with very high resolution, and basically you're doing, hey, the pattern is slightly off here, right? And now I can identify this as we have a potential problem.
Exactly. So in this image, on the left-hand side, you're seeing the actual wafer image. This one has a pattern, these regularly spaced dots. This is actually a calibration wafer. Occasionally, there'll be defects that are of that same brightness. So we see a bright white pixel. If you use a threshold, you're going to classify this bright white pixel and this defect pixel as a defect because it's the same intensity. It's the AIML that comes in and we can teach it what are the defects and tell it to ignore what are features. And that's really where we can use that AIML to get a better analysis on the package.
Brian, when did all the effort on acoustic really begin to pay off? I mean, this has been around for a very long time. You think about acoustic, this goes all the way back to sonar, right?
Yeah, I mean, we still use terminology from the sonar days. So we talk about A scan, B scan, C scan. Those were, that's what they were using in the submarines for sonar. The first acoustic microscope was roughly 40 years ago. So really, it's when we got into the higher frequency, up into the 300 megahertz, getting that resolution down to 5 microns. Kind of our champion resolutions around 3 microns. That gives us a much greater ability to find those smaller defects. And in today's market, with everything getting smaller, you really need that high resolution to see those defects in the customer samples.
Brian Schackmuth, thanks for a great explanation.
Yeah, thank you.